I'm Dr. Ben Newman. I'm a coronavirus researcher. And I thought today it would be worth mentioning the new variant BA.2. It's like BA.2. This is one that is getting some press right now, and there are some things out there that are not quite correct, and some other things out there that are correct. And in general, I want to use this as a way to say, all right, how do you like what's the best available way to dissect one of these strains? How do you look at a new sequence and figure out, is it bad, is it not so bad, what's it gonna do? And so there are things you can do and can't do. You can't tell by looking at a sequence whether it is going to be mild, and honestly, I that's a word that gets thrown around a lot and I don't think has very much meaning. It's very difficult to actually do the tests in a way that would tell you if a virus is less likely to hospitalize or kill you. And you're not going to pick that up from the sequence. That's a thing you're going to have to figure out from hospitalization numbers in very large, nicely controlled, statistically valid surveys. So that's out of the question. But you can tell things like, does it have a lot of mutations in the same way that Omicron does that would make it resistant to antibodies and prior vaccination, something like that. Oh, there we go. We just updated. Neat. So, first off, we're going to, I don't know if they say it GISAID or GISAID. Yeah, but this is one of the sites that is tracking the variants. And so the variant they're tracking here is Omicron in general. As you can see, it's everywhere. And if we go down here, I think the interesting thing is we're at about 2/3 Omicron pretty much everywhere around the world. Interestingly, though, look at that. It leveled out and actually maybe went down a little bit in Africa. So Omicron may not completely take over if we take Africa as the test case for what's going to happen elsewhere. And it'll be interesting to figure out, all right, what are some of these other things that are maybe going to push Omicron out? Because that's the way it is with viruses. There's always somebody waiting to take the throne. It's like a great big game of I'm the king of the castle and you're the dirty rascal, or king of the hill, or whatever you want to call it. So let's look. The first place we can look is over here. And so this is where I went for a insight into, all right, what is this BA.2? Because I thought I knew what it might be, but it's always good to have a sequence. And so all I did was Google BA.2 and genome, and I scrolled through a couple of papers until I got to this one, and then this one actually has some sequences, and so there will be little numbers, these EPI, ISL, and then a number. That's the thing that you can look up on the GISAID website, and so you can go see that, or you can actually look up the clade BA.2 if it's a clade that's officially recognized, which this one is. So this is just talking about a case that popped up in China, and they are correctly saying that it is a lineage of the Omicron variant. And so here is why they say that. And they are correct, by the way. So we got to blow this up a little bit. Okay, so we got a family tree here. And so if you look down, everything on this branch that's covered by this bar, so all of those would be considered beta. So when you're reading a tree, what you want to do is you want to figure out where is the branch point. And after a certain point, everything downstream will be called a particular name. So in this case, all three of these join up right here. And so you can say this little line right here, or this little node where those two split, everything downstream of that is a beta variant. So, okay, neat. And so delta, all right, is all of these, and I think you could call B1617.1 delta if you were being charitable. So that's fine. So we can say that everything downstream of this branch is going to be delta. And then you go up here, you've got your Omicron way out here in left field, top field, whatever this is. Yeah, left if you tilt the graph over. And so these are the original Omicrons. These are the ones that first gained attention. Since then, though, there are these other things. And so we've got Omicron BA.1, Omicron BA.2, Omicron BA.3. Now, the way they've done this particular graph, it would appear that Omicron is coming, or Omicron BA.1, 2, and 3 are coming out of this group. And so if you look who's in this group, you've got your gamma and you've got alpha down here. So this is like, think of it as the gamma and alpha group, which also contains some of these things, which are Omicron, and these others. Now, I don't think this is the best way to show this tree because these are actually branches that come from the same sort of root as this one. So it's like a tree that you're looking at, I don't know, a little bit sideways, and we've selected the middle of the trunk instead of the root of the thing as the place that we're calling the root. But if you were to look in a lot of the news reports, they're saying that Omicron itself came from Delta. And that is not supportable by this tree as far as I can see. As Delta's over here, and so it's everything downstream of this branch. And for Omicron to have derived from Delta, it would have to be a branch from one of these, and then we would have to label that as Omicron. All these labels are somewhat arbitrary. We're picking a line and saying, okay, everything after this, we're going to call this particular thing, and we do it because it's useful for keeping track of what the virus is doing. But within any one of these branches, delta, you'll rarely see two deltas that are genetically identical at every single position. Same with Omicron, same with everything. Yeah, it's a virus that changes, and so the best we can do is kind of draw a little moving dotted line around groups of interest that seem to be growing. Wherever there all of a sudden are a lot more branches appearing, that's a thing that we want to focus on, and so those are the ones that get names. Yeah. All right, fine. Now, let's go a step further over here. Okay, so that's our GISAID page. If you were to make a login, you can go into that, and I believe they'll let most anybody do that. And then you log in, and you can say, all right, I want to search for, and so I put in the lineage BA.2, and sure enough, there we go. We've got 13,000 virus genomes that belong to this lineage right now. And then what I did was I looked through all of these, and so if you have a little dark triangle, that means big problems, and so we're kind of missing about 6% of this sequence, and so I don't want to use that one as my basis because a lot of the missing parts tend to be in the spike, and it's because there are genetic changes there, and the way a lot of people get these sequences is with a technique that it's basically doing a lot of little PCRs. So you have a lot of little handles on the genome that you're trying to grab, and you read what's between the little handles, basically. There are enough changes in the spike, all clustered together, that some of those PCRs grab and miss because there's no handle in there because it's changed. And so you end up with gaps in the part of the genome that you most want to know. The little squares are not quite as bad, and the little circles with an I in it instead of an exclamation point. And I don't know, you got to really look to see that it's an I, like for information. Those are actually fine ones, and so I picked one of these actually picked an Austrian sequence, one of these. And we can take it over to this thing. And so this is NextClade, and so it's showing a different version of the tree with a lot more branches on it. And in general, if you can make a tree with more branches and the branches are all different to each other, it's going to be a better tree, but it's going to take your computer, a little bit longer and a lot more little computer tears to actually get there. So you can see on this one that your deltas are up here, and we don't really care about those so much, but your omicrons are everything downstream of this little orange branch. So here's the long branch where we didn't know what's going on. Here's the original omicrons, and you can see them here between 50 and 60 mutations. Here are the BA.2s down here. And you can see they're another branch. They branch off from Omicron at this point, but there isn't a sequence until we get there and until we get there. So these are things that we're changing outside of the reach of genome sequences. So they were changing in a place where there wasn't much genome sequencing. And now that we have multiple branches around Omicron, all of them connecting up at a point, about 15 mutations before Omicron, it looks as though this is maybe not a single event, but part of a lineage. That this is a virus that's been spreading somewhere. Perhaps Africa, not certainly, but perhaps Africa, where there was, basically a lot of opportunity for the virus to spread because of low vaccination and also basically nobody watching. Because each country tends to do its own genetic sequencing for the most part. Yeah, I don't know if it's a pride thing or just a division of resources thing. Anyway, you can go out here to this little dot, and that's fine. We can click it and open it up. And so this is the new sequence that I stuck in there. And here we go. These are all the changes. Now, that's a great little laundry list of changes. And so what do we do with these? Well, there are a couple that pop out. So if you're looking at the nucleoprotein, the N protein, that's one where we know there are these two parts. So the whole N is about 450 amino acids long. And there's two parts. So think of them as like that, like two little train cars connected up via a flexible bit in the middle. The adaptive mutations, the mutations that seem to make the virus grow better, tend to be in the little linker, and they actually tend to be in this end of the linker. And so they tend to be around 200 to 205. And so here you can see we've got two mutations in that 200 to 205 range. And these are both mutations that, at least on other viruses, have made this thing grow faster. So until we learn otherwise, we would say, all right, these look like changes that would give the virus a little boost, being able to grow more. I say, okay, fine, yeah. And I would say for now, don't worry about which changes are in there. Just assume if there are changes in that spot, probably it's going to be one of those. That's like a reasonable assumption in the absence of other facts and digging through the literature. Now, the other place that is worth looking, and where, everybody's looking, is the spike. And that's because we understand the spike a little bit. So there are three chunks of the spike, and I made a little chart right up here. This is how I would look at a spike and interpret what it's going to do. So the spike's got a couple jobs. It's got to get activated. And there are actually two activation sites, but one of them never changes. So we're just going to write that one off until the virus figures out a way to change it. I think the implication is that that site is pretty optimal, and change does not make the virus better. Remember that the virus changes randomly all the time, but it's only if a change turns out to be neutral or helpful to the virus that you will see the change carried on to the next generation. Otherwise, the virus is just crippled and then dies, basically. Because evolution is terrible. All right. So activation is number 2. The virus will sense when it's inside of a cell and will refold. That's like a triggering mechanism. And so that's down toward the tail of the spike. And the spike is about 1,200 and some amino acids long. And the other thing you want to look at is the receptor binding face. So this is the part of the spike that's actually going to stick on to your cell. And if there are changes there and the virus is still growing, that means the changes are either neutral or they help it get a better grip. I mean, right? Yeah, kind of makes sense. And you can wait for modelers and biophysicists to actually go out and confirm this. That's fine. But if you see changes in this area, which is the primary point of contact between virus and human cell, that tells you that probably, just, on the basis of probable cause, most likely outcome, probably these are going to be mutations that change the way the virus grips onto the cell. And they're probably not going to be changes that make it harder for the virus to grip onto the cell, in general. Yeah. So there you go. You got the chunk 438 to 506. The activation site is real small. It's around 680, plus or minus 5. And then you've got the sensors that are right down toward the tail, but not quite at the tail in that region. And we know where these are from other coronaviruses. And you can line them up and say, there we go, this chunk, roughly. and also from the structures. Anything before the first chunk is going to be a site where some antibodies can bind, but most of those antibodies are not going to stop an infection. This is just an area where the virus can soak up antibodies that will maybe slow it down a little bit, but really not do much. So in general, we can just say, you know what, let's not worry about those. We'll learn later if any of those end up being super important in an unexpected way. And in between these chunks, don't worry about those either. There are changes there, but the changes are very difficult to understand without testing. They're like changes that are not going to give a predictable outcome. So with this in mind, let's look through our new virus. So for an example, Omicron has 10 different changes between 438 and 506. So what do we have here? So here's the spike, and so find our 438, there we go, it's the first one. 1, 2, 3, 4, 5, 6, 7, 8. So we have a virus with 8 changes, and if you were to go and look up a list, all 8 of these are the same changes, I believe, or they're at least changes in the same position as you get in Omicron. So this is mostly Omicron. It's very Omicron-like, and it has a concentration of changes. Now, it only has 8, where Omicron would have 10, so maybe you would have a little bit better chance of binding it with antibodies from an old infection or from vaccination. It should be a little less likely to break through, but in general, it's pretty far out, and 8 changes in such a small little chunk is really a lot. Second, all right, let's look at the furin activation sites. So do we have any changes from 675 to 685? And we want to look for additions of the letter K, R, and H. And these are particular amino acids that could make it better. And so look, there we've got 679K and a 681H. So we've got 2 mutations in a row, 1 gap between them, that would both make this more activatable. And that is something that you also see in Omicron and in most of the variants. Delta, right back to Alpha, tends to even have one of these. So this is going to be a variant that is easier to activate, and in general, viruses that are easier to activate have an easier time getting into cells. That's an area where the virus can fail and can die instead of starting an infection, just fall apart. All right, and then let's look for this last chunk. So 1048 through 1162, and nope, I don't see any changes there. So this is not one with enhanced acid sensing properties. So there you go. This is a virus that looks like it should have an easy time getting into cells if it can bind to them. It has a lot of changes which seem to make Omicron reasonably able to bind cells. It has a lot of changes at the site where you would need to get an antibody to protect from infection. So it should break through some vaccination and some degree of prior infection. But overall, it doesn't have as many changes in those areas as you find in Omicron. So this is, Omicron light. And that doesn't mean it's going to be any milder than Omicron, for sure. It's just not more likely to break through immunity than Omicron was. And it's very much Omicron-like. That's the only thing that's relatively close. So if you're reading that it's Delta-like, that's just people that are misinterpreting a tree or looking at a not very well-made tree, I think. So there you go. That's how I would look at this one. That's what's going on with this particular variant. There are anecdotal reports that it's taking over in local areas, but really it's just kind of a relative of Omicron, and it doesn't look particularly different. When we get an Omicron-specific booster, it should work just as well against this as against Omicron, because they have the same part of the spike where you need to get those antibodies. So there you go. I think that's enough on this. This has been Ask Dr. Ben.